Okay, so I'd like to thank the organizers again for inviting me and for providing this beautiful setup. And I've been enjoying India a lot. So this is about joint work with Eyal Goren, and the paper was published last year in Compositio Mathematica. I forgot to bring the reference, but of course you can find it, and you can find it on the archive too. And this is about what I consider to be a new method to study the geometry of unitary Shimura varieties in characteristic P that can provide, in some cases, new insights that the usual approach of local models does not provide. And it's connected to some classical notion in algebraic geometry of foliations, and I'd like to start with just pure algebraic geometry in characteristic P. So the idea is this: you have an algebraically closed field in characteristic P, and you have a non-singular variety X, maybe affine, of dimension D. So you have its Pth transform, xp, so you can imagine x being given by some equations, and xp by the same equations raised to the power p, the coefficients raised to the power p, and then you have the relative Frobenius morphism, which is purely inseparable, and it has degree p to the d, and you'd like to consider factorizations of it as G composed with F, and this is a problem that even in the case of fields is very interesting, and in the case of fields it was done by Jacobson, and actually it's included in the third volume of his famous book Algebra, but as far as I know it's never being taught in school. So what classifies such things Y, so F and G, we want them to be finite and flat. Finite they'll be automatically, but flat, that's the important point. What classifies such factorizations, and there's infinitely many of them in general, is what's called a height one foliation. So if you look at the tangent bundle of X, okay, the tangent bundle of X has a structure of what's called a Peelie subalgebra, a Peelie algebra. So you can take two vector fields, sections, and you can take their Lie brackets, as you know, if you think of them as acting on functions. Or in characteristic P, you can take also the Pth iteration of the vector field. So that's an operation that was studied a lot, and together they form what's called a Peelie algebra, and a height one foliation will be a vector subbundle, so it's a subshift that's everywhere locally direct summoned, and which is closed under these two operations in the theorem, which in the birational case is due to Jacobson. And it has a funny history, I will not go into it, but it was done by Rudakov and Shafarevich in connection with some work on K3 surfaces, and then Eknath mentioned it, but actually dilemmas are due to some Japanese that I've not mentioned. It's pretty deep. There exists a one-to-one correspondence between height one foliations E on X and finite flat morphisms like this, through which the Frobenius morphism factors. And how should you think about it? Everybody knows that Frobenius, so to speak, is contracting, okay? And here this partial purely inseparable map F is contracting in certain directions and not contracting in perpendicular directions. And the foliation gives us the directions along which it is contracting. So some remarks. First of all, in such a situation, so the emphasis is, by the way, that E has to be a foliation and F has to be finite and flat. Okay, so Y happens to be also non-singular because regularity descends under flat morphisms, and G happens to be also finite and flat. This is what sometimes is called a miracle flatness. It's enough that Y is called Macaulay for this. So the situation is symmetric, and you can go on and on now, starting with G and factoring the morphism Y to YP and build a whole tower. And how do you make the correspondence? It's very easy. If X is spec A and you're given E, you take Y as spec B, where B is simply all the functions that are annihilated by E. And of course, this includes, in characteristic P, all the P powers, so it includes AP. Conversely, given F, you let E be simply those vector fields that are killed by DF. And if R is the rank of the foliation, the degree of F is P to the R, as you would expect. And what you can also guess is that you can always find around a point X in X a good system of parameters, Y1 up, U1, I call them, up to UD, so that the map from X to Y, formally locally, looks like the map written there. The first R you raise to the power P, and the D minus R, last ones you leave. Fine. So in this case, we shall call Y the quotient of X by the foliation E. And a related question, a related notion that arises in this situation is the notion of integral subvariety. So I guess you all know in differential geometry, in infinity differential geometry, or the reals say, the involutiveness of E by Frobenius theorem guarantees that you can integrate it, that you can find what's called an integral subvariety. And this integral subvariety need not be algebraic, even if the foliation is algebraic. So the same notion exists here. A non-singular subvariety Z is an integral subvariety of the foliation if along Z, E is really the tangent space of Z. Okay, so what do you imagine? Of course, its dimension is the rank of the foliation. And here are some examples, all in the affine plane. So if you look at the foliation, which at a point x, y is y d to the y plus dx, it's a rank 1 foliation in the affine plane. This is involutive. That's rank 1 is always involutive, but it's not p-closed. If you take the pth iteration of it, you get y d to the y. That's an easy exercise. So that's not a good example. If you take y d to the y plus x d to the x, it is both involutive and p-closed. However, it fails to be a subbundle at 0, 0. Okay? It's a subsheaf. It is a saturated subsheaf, but it fails to be a subbundle at 0, 0. And as a result, if you do this construction, you take y to be a spec of the kernel of this foliation, it will have a singularity at 0, 0. And another remark is that in characteristic P, even if you have algebraic integral curves, there need not be a uniqueness theorem, as we have in classical differential equations. All the curves a plus bx to the p are integral curves of the foliation, simply d to the x, in the plane, but there are infinitely many of them that pass through any given point. So this was a little chapter in algebraic geometry and characteristic P, and let's go now to the subject, which is unitary Shimura varieties. So I only consider unitary Shimura varieties with respect to quadratic imaginary fields, although in principle with a lot of more notation, maybe we could do it. We didn't do it for general CM fields. So E is going to be a quadratic imaginary field. M and N are integers, M less than or equal to N, and lambda is OE to the M plus N. And I consider lambda, the lattice, with the Hermitian bilinear form given by this matrix. So this is not the quasi-split thing. This is the unit matrix M by M, the unit matrix N minus M by N minus M, and the unit matrix M by M. It's not ones along the antidiagonal. So this gives us a group scheme over Z of unitary similitudes of all the matrices of size M plus N that preserve this Hermitian bilinear form up to a similitude factor. And the real points of it is the usual unitary group of signature NM. And then we fix an auxiliary level structure N, which, to rigidify things, I don't want to work with stacks, should be at least 3. A prime P, which is odd and unramified in E, either split or inert, prime to N. I take my Kp to be the hyperspecial maximal compact, the ZP points of this group scheme at P, and away from P, I take full level N subgroup, and K infinity, the maximal compactable center group, so except for the GM, which is a center, it's UN cross UM at infinity, and then I take my K to be K infinity, K upper P, K lower P inside the adelic point, and as you probably know, in this situation, there exists a Shimura variety defined over E. So E is the reflex field if M is less than N. If M equals to N, the reflex field is even Q, but we consider it always over E. It is a quasi-projective, non-singular variety over the field E. Its dimension is N times M. As a complex manifold, its complex points are identified with this double coset space, as usual, of the symmetric space GA over K divided by GQ. And Kottwitz constructed a smooth integral model of this Shimura variety. Maybe I should just say, just for those who are not familiar with Shimura variety, that this has a very long history. Of course, such complex manifolds were considered already by Klein, Poincaré, Siegel. Maybe they go back to Gauss in some cases. The algebraization was done by Bailey-Borel. Shimura and Denis gave an arithmetic model over E, and as I say, Kottwitz in 1992 constructed a smooth model over the localization of OE at P. Okay, it was constructed as a moduli problem of PEL type, and this particular Shimura variety appeared there as one of finitely many components. You may vary K, you may vary the lattice that I call lambda to get a few more. And what does this moduli problem classify? It classifies abelian varieties with extra structures. So for any R, which is an OEP algebra, you're looking at 4 tuples where A is an abelian scheme of dimension M plus N over R. Phi is a principal polarization. Iota is an action of OE as endomorphisms that has signature NM on the Lie algebra. So the Lie algebra R acquires a map from OEP. So the iota of A should act on a rank N subspace with the natural embedding, or natural map, doesn't have to be embedding, and on the complex conjugate on a space of dimension M. And since I'm excluding the ramified prime, you can really distinguish between the two. And then there should be a compatibility of the polarization and the endomorphism. The Rosati involution induced by the polarization should be complex conjugation. And eta, as usual, is a level N structure, which has to be symplectic in this case. And since this is a fine moduli space, everything is very nice. There exists a universal object, which I call script A. This is the universal abelian scheme over this integral model S. And we will be interested in the special fiber of the integral model, which is a nice variety over kappa. Kappa is Fp squared, is OE over, oh, sorry, I didn't say it that P is inert, but soon it will be inert. So if P is inert, kappa will be Fp squared. And Eknath and Ehud found a very nice stratification of this special fiber in characteristic P by the isomorphism type of the kernel of P, which is a finite flat group scheme at geometric points. So K is capital, not capital, but small k but not kappa, is an algebraically closed field like FP bar, and you're looking simply at the universal abelian scheme at such a point. So it has a kernel of P, which is a finitely group scheme, and there can be only finitely many choices, and they actually determine a stratification. And Ben Moonen and Vedhoen proved that in this stratification there exists a unique open dense stratum, which is called S-ord, but maybe I should warn you, it's what's usually called mu ordinary. And it has the following characterization. If P is either split in E, this is the case that we shall soon abandon because all that we'll be saying is trivial in this case, or N is M, then an abelian point, an abelian variety over a point in this open dense subset is ordinary in the usual sense. If P is inert and M is less than N, then it's easy to see that you cannot have ordinary abelian varieties in this modular space, but it is as ordinary as the combinatorics allows it to be. You should think about it this way, and this means that its p-divisible group is not a product of multiplicative by et.al., but it has these three pieces. It is OE tensor mu p infinity to the power m. So this is, okay, OE tensor mu p infinity is simply two copies of mu p infinity, but arranged in such a way that they have an OE action, and the same thing here for the et.al. part. And in the middle you have this G sigma, which G is the p-divisible group of a supersingular elliptic curve, which is height 2, and sigma means that I choose one of the two embeddings to give it an OE action, and yeah. Yes, always. Yeah, sorry. Always, when I talk about isomorphism type, always with the OE action. Yeah.
But if you forget it, you get the same certification.
No. If you forget it, forget the OE action. No, that's something different. No, that's bad. Yeah, exactly. It would be just like putting it into Siegel space, and then you have a stratification on the Siegel space, but it's not the same. No. You should take into the account. Yeah. No, if P is ramified, things really go wrong. I mean, Eyal and I are studying now. P is ramified, and this is a big headache, let me tell you. There's all this work of Papas, and yeah, that's a completely different story. Anyhow, right, so this is the most ordinary that you can get, okay? And this is the isomorphism type. I should say that in this case, the whole p-divisible group has this isomorphism type. You see, the Eknath strata, the stratification is by the p torsion. It's not the Newton stratification, and the relation between the two can be very difficult. But on the mu ordinary, on this big open set, actually the whole p-divisible group has this structure. Now, Moonen, in this case, okay, before Moonen. When P is split or M equals N, then we have seen in the first talk, the Serre-Tate theorem implies that at an ordinary point, in this case the mu ordinary or this open set is actually ordinary, the formal neighborhood of a point by the Serre-Tate theorem has a canonical structure of a torus. Now, all that I want you to take from this is that tori are isotropic. If you sit in the center of a torus and you look around, all directions look the same to you, okay? Like being in the Pacific Ocean and not seeing anything interesting around. When P is inert and M is less than N, Ben Moonen showed that at an ordinary point, a mu ordinary point, the formal neighborhood has a canonical structure, generalized Serre-Tate coordinates, but this canonical structure is of a torus torsor over the formal group of this supersingular elliptic curve to some power. And you see that the dimension of the base is n minus m times m, and the dimension of the group, structure group of the torsor is m squared. So this means that at your point, you see in the tangent space a distinguished subspace of dimension m squared, which is the tangent space in the direction of this group action. Okay? So life is not isotropic. And in fact, it's not difficult to show that these m squared dimensional subspaces, remember that the dimension here is n times m, they glue together to make a rank m squared foliation TS plus. So in other words, you have to prove that this thing varies nicely and that it's closed under Lie brackets and the p power operation. And now I can tell you our goals in this talk. So from now on, p is inert and m is less than or equal to n. You can take m equals n, but all that I'll be saying is trivial in this case. So the interesting case is m less than n. So first of all, I want to convince you that you do not have to study Munnen's work to construct TS plus. There is a direct construction of it. Secondly, unlike Munnen's coordinates, which are really unique to the ordinary or mu ordinary locus, you can extend TS plus to foliation. Okay, you want to extend it all the way to S. You cannot. You can extend it inside S quite a bit further to inner Eknath strata, but you reach a certain stratum where it acquires singularities, but then there is a process of blowing up. In fact, we will define another modular problem that has its merits and is interesting in its own sake. We call it S upper sharp, that exists only in characteristic P, and it sits above S, and you can extend the foliation nicely to this modular problem. But once you have and it's non-singular. Once you have a non-singular variety and a foliation, as in here, you can ask, what is the meaning of the quotient? So we would like to identify the quotient of S upper sharp by the foliation as a certain irreducible component of a Shimura variety of parahoric level structure. So this is like the x0 of P. So I guess most of you are familiar with this famous picture from the Lin-Rappaport of the classical modular curve x0 of P over Zp. So it has this nice structure where you have two strands, both of which are P1s, and one is the étale strand, the other one is the multiplicative strand, and they somehow map to x of 1. This maps isomorphically, and this maps purely inseparably in degree P. So this variety that I call S, yeah, this is the special fiber of this model. Yeah, of course, yeah. Generic fiber, you all know. This is the special fiber of this model. And the S0 of P is the right analog of this in this unitary case. It has been studied by Rappaport and Zink in the last chapter of their book, but we apply this notion of foliations to get this variety as a quotient of this S upper sharp that we construct, and thereby to obtain consequences for the singularity of certain irreducible components in S0 of P. There's many more than two in the general situation, but we single out two that we call the étale and the multiplicative component. And as I said in the beginning, these consequences, you're not able to get them just by the theory of local models. And then finally, we want to study integral subvarieties of this foliation, and we will find integral varieties of two types, Shimura subvarieties, embedded Shimura varieties of lower dimension of signature mm, and also this special Eknath strata of dimension m squared that I mentioned before, which is the last one to which you can extend the foliation before you have to blow up. It will just have the right dimensions. It's a very nice picture. So let me remind you first, so remember, no, I did not show, I'm going to show it now. No, these are goals. You see, this is goals. Okay, so TS plus was a byproduct of Moonen's generalized Serre-Tate coordinates. So Moonen had generalized Serre-Tate coordinates in this situation, which are not a torus, but rather a torus torsor over some formal group. And if you have such a situation, at the tangent space, you have a preferred direction. You have a subspace. Now, that's done point by point. So I didn't show it, but I just said that this thing that is done at every geometric point, little x, can be glued to give you a foliation. It varies algebraically, okay? It's a subbundle, okay, locally direct summand, and it is closed under Lie brackets and Peace powers. And this is what I call TS plus. But now I'm going to give a new construction. So for this new construction, let me remind you that don't confuse these Frobinii with this Frobenius, okay? This Frobenius is the Frobenius of the base relative to the field, and now I want to consider the Frobenius of the universal abelian scheme relative to the base. Okay, so over this X lies an abelian scheme, and I consider the relative Frobenius of that abelian scheme relative to S. Now, since this is an abelian scheme, you can consider the Frobenius of the dual abelian scheme and its dual, and you get what's called a Verschiebung. They're both isogenies of this family of abelian varieties. And by functoriality, V induces a map, Verschiebung induces a map by pullback that we call simply V. So this appeared in Banerjee's talk, right? You did it in the, I'm heading towards the Hasse invariant, so in this case. So this is V from the first Durham cohomology. So that's right, the first Durham cohomology is a vector bundle over S of dimension, rank twice the dimension of A, twice m plus n, to its P transform. And of course, it induces the same thing on the Hodge filtration inside, which I call simply by omega. And remember that we have the action of the endomorphisms, so omega breaks up as a direct sum of a rank n piece and a rank m piece. Okay, so together this is rank twice n plus m, this is rank n plus m, but it breaks up as a direct sum. Each is a vector bundle on which OE acts via the identity or via the complex conjugation. And V, if you follow the way it commutes with endomorphisms, should map P to the Peace transform of Q and Q to the Peace transform of P. Okay, so V is this n plus m times n plus m matrix, but it's really given by two blocks, one size n times m and the other one size m times n. Okay, so this looks like the situation. There's 0 here, and in some coordinates it looks like a matrix like this. So I call these VP and VQ. And now what I can do, and this is, by the way, I should have given credit here. This was done by Marco Bernicol and Goldring, and later I think generalized by Goldring and Koskivirta to other situations. So these definitions of Hasse invariance in the unitary case. So you can look at VQ. So VQ goes from Q to PP, remember? This was VQ here. It was maybe this matrix. And then you can follow it by the Peace transform of VP to get to QP squared. And since m is less than or equal to n, you have the hope of getting a matrix that's invertible. So you take its determinant. This is a map of line bundles this time. L is the determinant of Q. From L to L, twisted by Frobenius p squared times. But for line bundles, this is isomorphic canonically to the p squared power of L. So altogether, you can think of this H as a section of L to the p squared minus 1, right? It's a homomorphism from L to L p squared. So this is very similar to what you get in the classical situation, a section of L to the p minus 1. Here it's a section of L to the p squared minus 1. And this is the Hasse invariant. It's a modular form. And it's a lemma that's not too difficult to show, that the ordinary locus is exactly where this Hasse invariant doesn't vanish. However, the key observation is the following. Of course, if the Hasse invariant doesn't vanish, this has rank m, this has rank n, which is bigger than m, and this again has rank m, then this has to be injective and this has to be surjective. But this can still be injective, and if its image here, which is of rank n minus m, meets the kernel of this one, which, the image here is rank m. If it meets the kernel of this one, which is rank n minus m, if it's not a complement to it, you can have the Hasse invariant vanishing and still the first map being injective, or rather the second map having kernel not bigger than n minus m. Okay, so each of the separate maps can be as non-degenerate as you want, and still the Hasse invariant may vanish. This means that what I'm going to define now, the kernel of Verschiebung on the sigma part of the cotangent bundle on P, which on the ordinary locus will have rank n minus m, will still have rank n minus m quite a long way further beyond the ordinary locus, where the Hasse invariant already vanishes. So remember this. At the moment, we're only over the ordinary locus. Okay, so I'm defining P0 to be this rank n minus m subbundle just over the ordinary locus at the moment. And now we have to recall a certain relation that exists between P and Q and the cotangent space of the base. So this is the same relation that in the usual case of modular curves gives you the relation between modular forms of weight 2 and differentials on the base, okay? Everybody knows this, but what's hiding behind it is really deformation theory and the Kodaira-Spencer morphism. So the Kodaira-Spencer homomorphism is an isomorphism between P tensor Q and omega S. And of course, this works not only in the special fiber. P is n-dimensional, Q is m-dimensional, S is n times m-dimensional, so the numerology works out well. N was greater than or equal to m. Yeah, I mean, you just have to choose. You just have to call one of them. You have to just decide which is bigger, and you call it sigma, and the other one sigma bar. Oh, because right? No, there's a choice here because that's what's interesting. You could do the other way around, but then you would necessarily get something that's always singular because you would go from n-dimensional to m-dimensional and back to n-dimensional. That's no good. No, absolutely. There is the Hasse invariant has to be defined this way. Yeah. You're right. But in terms of just this, there's no loss of generality in assuming that n is greater than or equal to m. Okay. Yeah. Okay. But once you chose it, you have to, you're right. So, so since I have this distinguished P0, it makes sense to talk about the P0 tensor Q being of dimension n minus m times m. Okay, this is n minus m, this is m, so that's n minus m times m. Taking Kodaira-Spencer off it, so that's a subsheaf of omega, and you take the perp to get a subsheaf in the tangent bundle, which is dual to the cotangent bundle, and this is going to be what I call TS plus. So here is the theorem. First of all, so you see this has a very nice construction, which I already pointed out would tautologically extend whenever you can extend P0 as a subbundle, and this goes beyond the ordinary locus inside further Eknath strata. So first of all, this is a height 1 foliation of rank m squared. So you have to prove that it is basically closed under Lie brackets and p power operation, and that it does coincide with the, what I told you before from Moonen's point of view. Okay, so I will not go over the proof of it. Let me just say that you have to understand how Kodaira-Spencer is defined from the Gauss-Manin connection. You have to understand relation between various pairings on H1 de Rham. And finally, it boils down, the involutiveness boils down to the fact that the Gauss-Manin connection is flat. And being closed on the P operation is a little bit more subtle because you have to consider what's called the P curvature of the connection, which the P curvature of the Gauss-Manin connection doesn't vanish, but luckily there's a theorem of Cartier that tells you that it does vanish on the kernel of V, which is what we want here, that's the P0, and from this you get the result. So it's not a very difficult proof. Definitely easier than Moonen's. So now we come to the point where we want to understand the quotient. We're still only over the ordinary part. Okay? So if we were doing this case, this is the case, of course, of U11. It's not interesting, but we would be outside the supersingular logos. And in general, we're over in this open Zariski set. And I want to define the Shimura variety as 0 of P. And for this, remember that lambda was our lattice OE to the power n plus m. And the Hermitian form had a very specific shape with this matrix that I described at the beginning in blocks. So I take lambda prime to be the lattice inside lambda generated by PE1 up to PEM, and then I take the rest as they were. Lambda double prime to be the one with PE1 all the way up to PEN, so n is bigger than m. And then I have lambda contains lambda prime, contains lambda double prime, contains p times lambda, but I actually localize it p. I tensor with zp over z. And this is a chain of lattices, and I let K0p be inside the hyperspecial maximal compact, be the stabilizer of this chain of lattices. So if you know the Brouwer-Tate building, this would be a stabilizer of an edge. But the edge would be between a hyperspecial maximal compact, a hyperspecial vertex and a non-hyperspecial vertex in the building. And in this case, an integral model was defined. Okay, so this is another Shimura variety, but it has bed reduction. Just as in classical modular curve of level gamma 0 of P, it has bed reduction. And Rockwood Singh, in chapter 6 of the famous book, worked out an integral model for all parahoric level structures, in particular to this one, and I denote, as usual, by script S0p the integral model, by S0p over kappa its special fiber. And this now becomes very subtle. It's singular, it has several components, this special fiber, several irreducible components, but Geltz, nevertheless, proved the following theorem. First of all, it is, the integral model is flat, okay? And the special fiber is reduced, and each irreducible component is normal and Cohen-Macaulay. Well, this is as close as we can get in this setup to being non-singular. It need not be non-singular as it is here, of course. Here you see there are singularities, but each irreducible component in itself is just a smooth P1, right? Well, at least if you have some rigidifying tame level structure. And what is the modular interpretation of this S0 of P? It classifies very much like the classical X0 of P, 4 tuples A as before, which I just write A underline, and H, a subgroup scheme H. H is a finite flat subgroup scheme of the kernel of P. It has rank P to the 2m. It's isotropic for the Weil pairing associated with the polarization. It should be OE stable. And you think that this is enough because it relates to all the structures, But if you just impose these things, you get a representable modular problem, but that is not flat. There are some bad components in the characteristic P fiber that sort of stick out and you cannot approach them from characteristic 0. And to define something that's flat, you have to add another notion of the group scheme being Raynaud, and this technically means that this Dieudonné module at every characteristic P geometric point is balanced. Now, this is not their terminology. We learned this terminology from the thesis of Yoel Belaish, who did the U21 case only in his thesis, Picard modular surfaces, but we borrowed this terminology in general, and it's a little lemma that these conditions are equivalent to what's in the Rappaport-Zink book. So remember that at an ordinary point, you have this structure for the kernel of P. Okay, we previously wrote it for the P-divisible group, but this, of course, is inherited by the P torsion. And you remember, we have to take a subgroup which satisfies all these things, which is of rank P to the 2m. So in general, it will be mixed. It will have a little bit from here, a little bit from there, and a little bit from here. But of course, there are two extreme cases. One, when you take this whole subgroup OE tensor mu P to the m, which is of the correct rank P to the 2m, which is OE invariant and isotropic. This would be called the multiplicative case. And the other case where you take this subgroup, which is étale. So we denote by S0P ORD the open subset of S0P lying over S ORD. So in this classical case, it would be just this picture minus the supersingular points. And we write little m and little étale as subscripts for the irreducible components. They happen to be irreducible components of this part S ORD, where H is of multiplicative type or étale. And then once we do this, we drop the ORD to denote there's a risky closures in S0P. So here this would be like taking each of the P1s minus the supersingular points and then filling in the supersingular points, the missing ones. But of course, what we do here is much, much more complicated, and we really a priori do not know what's happening when you take this risky closure of these irreducible components. So here is the theorem that identifies this quotient S0P étale ORD. So, sorry, this leaf, or so to speak, this irreducible component only over the ordinary part as the quotient of S ORD by this foliation. So the theorem says that if you associate to this foliation that we constructed the quotient in the sense that I described at the beginning of the talk, then the quotient is just this part of the ordinary locus in the parahoric level Shimura variety. And you can write down functorially how you get it. Let's not get into it. You also have a map going backwards from here to here, which is just forgetting the level P structure, right? So you can go from here to here by projection. And if you compose these two maps, this map is of degree m squared. The other one of forgetting the level is of degree 2n minus m times m. When you compose them, you get a map of degree p to the 2n m, which is just Frobenius squared. Of course, Frobenius does not take you from S0P to itself, only Frobenius squared, because the field of definition is Fp squared. And on the multiplicative side, on the multiplicative component, just as we had here, the projection is an isomorphism. Fine. So now we come to the next task of extending this foliation all the way to S. So I already hinted that it would extend by the same definition without having to go through Moonen's theory of generalized Serre-Tate coordinates whenever this P0 is of the right rank, right? Because this would still be a subsheaf of the same rank, and it's easy to see that it would satisfy all the good conditions, and this would be a foliation. So we let S lower sharp be the open subset of S where this holds. So here's the proposition. S lower sharp is a union of Eknath strata, contains the largest one, which is S ordinary, but also a unique smallest one, which we call S fol, in honor of the foliation, which is of dimension m squared. So they go from dimension n times m to dimension m squared, and the foliation Ts plus extends over S sharp, but cannot be extended, becomes singular if you want to go further. So here are some pictures, what happens in two examples. So if m is 1, so Shimura varieties of signature n1 are much, much easier than the general case. In this case, there are just n plus 1. This is not the picture here. I just try to imagine it. There are n plus 1 Eknath strata arranged linearly. So of course, I didn't tell you, but as in any stratification, the order relation is being contained in the closure of the previous one, okay? So each one, its closure contains all the ones that are below it. And S lower sharp, in fact, will be the union of n of them. So only the very last stratum, the so-called superspecial points of dimension 0, is not in S lower sharp, so you can extend without meeting singularities, the foliation all the way to the superspecial points from the top dimension, which is n, to dimension 1. Let's take this case, nm equals 4, 2. So there's some combinatorics of permutations of what's called nm shuffles that tells you, this theory of Moonen, tells you how the Eknath stratas are arranged. So here is the diagram. This is the ordinary one. The next one of dimension, so the dimension here is 8. This is dimension 8. There is also a unique stratum in dimension 7. There's 2 in dimension 6, 2 in dimension, got to 6, 5, 4, 3, 2, 0, 1, 0. And this is the superspecial points once again. And the ones that participate in the game are the ones that are highlighted here, okay, all these. And this is S fol, okay? So you see and the arrows are the relation of being contained in the closure. So as you can see, it gets very combinatorially very complicated. In this case, S fol is of dimension 4, which is m squared, 2 times 2. Fine. So how do we blow up S? Okay, as usual, if you do not have a unique P0, you add this P0 that you want to be unique to the data that you want to classify. So I define a new modular problem only in characteristic P that's called S upper sharp. It lies above S, and it's isomorphic to S as long as you are over S lower sharp. And it classifies these 4 tuples as we had before, and P0, which is a rank n minus m subbundle of the kernel of Verschiebung on P. So you see, it only makes sense in characteristic P because by definition it uses Verschiebung in its definition. And the theorem is this modular space is smooth over kappa, first of all. So this is a non-trivial theorem. And it happens that this is an example of something that in algebraic geometry is called, we didn't know this, it's called incidence scheme of Grassmannians. So this is in the modular spaces theory, in algebraic geometry in general, there is such a notion, and there's a criterion for an incidence scheme of Grassmannians to be smooth that we found in a book by Harris, and luckily we can prove using the specific case that we have at hand, the modular interpretation, that this is the case. So this is very nice. The morphism from S sharp to S, forgetting the extra structure, is irreducible in the sense that the preimage of an irreducible component of S has many irreducible or even connected components, is irreducible. It's by definition, it's isomorphism over S sharp, where the P0 is dictated, right? Because the kernel of V already has rank n minus m, not larger, so P0 must be the whole kernel of V. And the word tautologically is not a good choice of word. I should change it to canonically. Okay, you would think that, okay, use the same Kodaira-Spencer construction with this P0 tensor Q to extend the foliation. The problem is that over S upper sharp, the Kodaira-Spencer is defined, but is not an isomorphism anymore. Okay, you lost the property of Kodaira-Spencer being isomorphism, so you are afraid that it's not going to work. It nevertheless works. Takes some little effort. And so the situation is this: we have extended this foliation all the way, but not on S, but over this S sharp. That's a successive blow up. And just as an example, remember in the case of UN1, where M is 1, S lower sharp was everything but the very final points, super special points, where the abelian variety is actually isomorphic to products of supersingular elliptic curves. And S sharp, upper sharp, sorry, is the blow up of S at these super special points. Just the usual blow up. So now we can extend the theorem describing this parahoric level Shimura variety as the quotient of the ordinary part by the foliation to S sharp. So now I've got this S sharp, we've got the foliation, and we can define the quotient of S sharp by the foliation, and it is what you think it is. So the isomorphism, well, first let's treat the trivial case of the multiplicative component, the multiplicative ordinary component, which was isomorphic to S ord. So this isomorphism extends to an isomorphism between the multiplicative component and S upper sharp. So you can find this S upper sharp as sitting as one of the components of your parahoric level Shimura variety, the special fiber of your parahoric level Shimura variety. So that's very pleasing. And if you look at the étale component, then the quotient of S upper sharp by this foliation is now the Zariski closure of what we had over the ordinary situation. And here are consequences. So first is that the irreducible components S0pm and S0p étale are non-singular. So you remember previously each of the irreducible components, and there are many mixed components, as I said, that are partly multiplicative, partly étale, where this group H is not one of the two extreme cases. All that they were by Gertz, all that we could prove, and I believe that's all that they are, is they are normal and Cohn-Macaulay, but normal is, yeah. And here these two extreme components are actually non-singular. And I want to stress that this is something that you will never be able to prove by the methods of Gertz from the local model point of view, because the local model doesn't see Verschiebung, doesn't see the things that were put into here. And in a way, you're really locally at a point somewhere, and you do not know, if you're not over the ordinary part, you don't know how it came from far away from the ordinary part via this procedure of Zariski closure. Okay, so let's go further. Yeah, maybe I'll just say one word before I go to integral some varieties. The proof of this uses Gertz theorem, because in a way we know that we have a foliation here, okay? So we know that we have something, let's denote it by y tilde, and rho, and we know that this is flat. Because this is a foliation, the quotient is a flat map, finite flat, of course, and this is non-singular. Okay, so this was from this theorem of Jacobson generalized, which is non-trivial. Now we also know that we have a map like this to S0p étale, and we know that that over the ordinary part, this vectors, and over the ordinary part, this is aberrational isomorphism, and we know that this is normal. So you're right in the setup to apply Zariski main theorem. Zariski main theorem tells you that if this is a birational isomorphism and this is normal, then this should be an isomorphism. So what you get is that this is this, therefore non-singular, and that this map is flat. Okay, so in the last 5 minutes, I want to go quickly over the issue of integral subvarieties. So this is a completely different story, and we have the following theorem. We found two types of integral subvarieties. First of all, embedded Shimura varieties of signature MM. So think of the classical case, I'll give it in the last slide as an example of signature 2, 1. So n is 2, m is 1. That's the first interesting case. Signature 1, 1 would be either classical modular curves or an inner form of U1, 1, which would give you classical Shimura curves. And they are integral subvarieties of the foliation. But you also have this characteristic P curve in the case of U2, in the case of Picard surfaces, in general subvariety of dimension m squared, which we called S-fol, this Eknath stratum, which also is an integral subvariety. And the proof of 1 is rather easy. It's somehow the compatibility of all our constructions with changing the group. So not too difficult. The proof of 2 is very subtle. It's quite a lot of computations with Dieudonné modules and deformations. So you really have to believe in it and then forget about intuition, just work hard with Dieudonné modules and linear algebra or semi-linear algebra, and then it comes out. And well, I don't know how much I stand behind this conjecture, but maybe these are the only integral subvarieties of TS plus. Why? Simply because these are the only ones that we could find. But even for U2, it's an interesting question. So as a last slide, let's just see what this means in the example of U2. So let me draw a few pictures. So U2, these are famous. Shimura varieties for U2 are very famous. They're called Picard modular surfaces. There was in Canada long ago a big conference by Langlands and Rappaport and others, Krishnan, that resulted in a big book on this. It's one of the first test cases for many conjectures on the trace formula. So there's a lot of work that has been done. Maybe after modular curves, this was the case that was studied the most. This and the Hilbert modular surfaces, of course. So these Picard modular surfaces, the characteristic P fiber, the generic point is mu ordinary. So this is what we called S ordinary. But then you have certain curves that intersect. This is the next Eknath strata, what we call, it's supersingular. It happens to be supersingular. The Newton polygon that happens to be of slope 1/2, constant slope 1/2. But in general, Eknath strata are not Newton strata, but here it's still simple enough. We call it general supersingular, and the singular points where these intersect are the superspecial points. And geometrically, this was done, of course, not by us. These curves are Fermat curves of degree p+1. It's very nice. This is, by the way, the S-fol, okay, in this case. So S-fol, of course, here should be m squared dimensional. So inside two-dimensional thing, you should have one-dimensional. So these are these curves. So you can extend the foliation to them, but not to these points. S sharp, as I said before, in general in UN1 one case is just a blow up here. Now, if you already know that the foliation is tangential along these Fermat curves to the Fermat curves, you see from this picture that you cannot extend it across here, but once you blow up, of course you can extend because these intersections are transversal, so you only have to blow up once. And in fact, you can say more, these P1s that you have, if you worry about field of definition, can be canonically defined over kappa, even if these supersingular points, because maybe of tame level structure, are not defined over fp squared. The P1s, somehow they come from level 1, are defined over fp squared. And then you have this canonical coordinate and the almost canonical, and where these Fermat curves intersect, the blown up points is at point zeta, where zeta to the p plus 1 is minus 1. On the other hand, you also have embedded Shimura varieties. Okay? Maybe this is an embedded Shimura variety. It also, in characteristic P, approaches these points, but at a different slope. So one last thing that's not on this, but we have, this is work that was done 2 years ago, already appeared. We have another work where we treat a completely different issue, certain theta operators on unitary Shimura varieties, but somehow it's related to this via the following question. You see, you have this foliation and you have these Eknath strata, and the foliation at an ordinary point, of course, is contained in the tangent space there, because the tangent space there is everything. And also at this last Eknath strata, S fall, which is of dimension m squared, it's also contained in the tangent space to the foliation, to the stratum, because it's equal with it, okay? Both of dimension m squared, and I proved that this is an integral subvariety. What about all the intermediate ones? Remember this picture that I had? Oops, sorry. Here. What about all these in between? Is the foliation always contained along a stratum inside the stratum? So a crucial computation that we did in this paper that I'm talking about, the one after this one, is to prove that this is also the case here in this next stratum that we call the almost ordinary stratum. And this was very important for the analytic continuation of the theta operator that is encountered in the theory of p-adic modular forms and mod p modular forms. So there remains the question of what happens in all of them, but it seems so far that the technique that we have is each time to make a computation with Dieudonné module. We do not have a conceptual understanding of this question. Okay, so thank you very much. That's all.